Alright, hello class. In this video we're going to be talking about related rates, and this is one of those topics that gives a lot of people trouble when they first learn it. But what you really need to know about it is it's essentially just implicit differentiation, okay? And it's really in the name, related rates. Okay, so what are related rates? Well, related rates are essentially analyzing scenarios, usually physics-based scenarios, where the rate of one quantity is related to the rate of another. Okay? That might sound like that's what we've been doing this entire time, and it kind of is. The only tricky part is we're going to be doing this implicitly because we are going to be talking about how the rate of one thing with respect to time affects another thing with respect to time. So these will all be derivatives with respect to time. Okay. So typically all with respect to time, which we'll call t. So we're looking at the derivative with respect to t. All right, so in situations, we've been looking at things like, okay, y equals f of x. This tells us that dy by dx is equal to f prime of x. Now what we'll be looking at with related rates is a little different, because instead of saying y is equal to f of x and then differentiating both sides with respect to x, we're instead differentiating both sides with respect to t. Right? So we'll have the derivative of y with respect to t is equal to the derivative of f of x with respect to t. So now that the variables here don't match, we're basically doing double implicit differentiation, or double chain rules, right? So this is going to be a dy dt, nothing, big here, no big changes here. But here, this would be something like f prime of x times dx dt, right? So we're going to have basically double implicit differentiation, or triple implicit differentiation. Okay, so instead of just doing a dy dx, whenever you do a derivative with respect to y, now you're basically going to do one of those for any variable you have, because we're differentiating with respect to t. Okay, I think it's much easier to explain this kind of stuff through examples. So let's look at a fairly basic example. All right, so I always like to start with a circle. And I don't like to put a super crazy physical example on top of everything to start with. Let's just consider a circle. And it has a radius that is increasing in length over time. So, right, so say we have this circle here. And let's say, whoops. Right, let's say this is its radius. And this is, say, at time. We'll call this radius 1, and this is at time, let's say, 1 minute. All right, and it's increasing at a certain rate such that at, say, times 2 minutes, it's now reached this next length. Okay, so now its radius is at, say, r2 at t equals 2 minutes. Now, as r increases, in order for this to stay a circle, right, to continue being a circle, the circumference of the circle also has to be increasing, as does the area. Okay, now hopefully that makes sense. If we were to look at it on a graph, say like this, here's my radius, here's my circumference, and as the radius is increasing, so does the circumference. And not only is it also increasing, it increases in a way that is related to r. which hopefully makes sense because the circumference is completely dependent on r, and r is changing with respect to t. Okay? Also, at the same time, okay, as the radius increases, so does the area. You can see that I'm representing the area as these dots. The area is also increasing, and it does so in a way that is related to the radius. Okay, so not only do the circumference and the radius increase, the circumference and the area increase, they do so in a way that is related to the radius. Okay? So that's why these are called related rates, because, well, they are rates that are related. It's really that straightforward. Now, how we find these related rates is we basically start with a formula that relates the quantities, and then we differentiate implicitly with respect to t. Okay? So, and here I've shown, or I've underlined the word relates, because that's the idea. We always try to find a formula that relates the quantities in question, and then we differentiate implicitly with respect to t. Now for a circle, right, so say for our circle here, I won't make it perfect this time, but the circumference and the radius of a circle are related in the following way. The circumference is equal to 2 pi r. Okay? And then similarly, if we want to compare or relate the area to the radius, the area is pi r squared. Okay? So now, if we differentiate both of these things with respect to t, all right, we'll start here. The derivative with respect to t of their circumference is going to be equal to the derivative with respect to t of 2 pi r. Okay, and we're assuming that the radius changes over time, so the circumference must also change over time. Okay, so when we differentiate, it really just comes down to dc by dt, okay, is equal to 2 pi, and then the derivative of r with respect to t is literally just dr dt. Okay, so this here, what we started with, this is a formula that relates just the quantities themselves, the circumference to the radius. This formula relates the rate of the circumference to the rate of the radius. Okay, so just to write that down, c equals 2 pi r, that relates the quantities of c and r. So it relates the circumference to the radius. This formula, dc by dt is equal to 2 pi dr dt, relates the rates of c and r. So it tells us how the rate of the circumference relates to the rate of the radius. Okay, so, all right, so if the radius is increasing by 10 centimeters per minute, then the circumference increases by, well, now we just use this formula. dc by dt is going to be 2 pi times dr dt. Well, that's what this 10 centimeters per minute is. If the radius is increasing by this much, well, this tells me that dr by dt is 10 centimeters per minute, right? The dr, r is a length, centimeters per t minutes. Okay, so when we put that in, this is 10 centimeters per minute, it comes out to be, well, 20 pi centimeters per minute. Okay, so if the radius is increasing by 10 centimeters a minute, the circumference is then increasing by 20 pi centimeters per minute. Okay, and just to verify this, say at, let's say at t equals 1 minute, the radius is equal to, let's say 8. okay, 8 centimeters. So then that means when t is equal to 2 minutes, so 1 minute later, the radius should be 18 centimeters, right? Because the radius is increasing by 10 centimeters per minute, so that means from 1 minute to 2 minutes, so minute 1 to minute 2, the radius goes from 18 centimeters, or from 8 centimeters to 18 centimeters. Okay, well then the circumference, which is just 2 pi r, in this case it will be 16 pi. Okay, and then in this piece, right, when r, in minute 2, when r is 18, we'll get 36 pi. Okay, now if we say call this R1, R2, C1, C2, then delta C, okay, the change in the circumference, C2 minus C1 will be 36 pi minus 16 pi, which is going to be 20 pi. Okay, and these should also be in centimeters, but that's essentially what we're saying, that when after 1 minute, when we go from minute 1 to minute 2, the radius increases by 10 and the circumference increases by 20 pi. Okay, that's what related rates are all about. Okay, that's essentially what they're doing, is they're taking two quantities that are related and then showing how their rates are also related. So one thing you might notice is that the formula for the related rates per circumference are exactly the same as just the normal formula, right? C is equal to 2 pi r. The derivative of C is equal to 2 pi derivative of r. That's actually pretty nice, but it doesn't always work out that way, right? For example, when we do it here with the area, so if we take the derivative with respect to t of A, that's going to be the derivative with respect to t of pi r squared. Okay, so here, dA dt, that's just what that side's going to be. Here, the pi sits there, it remains the same, but now we differentiate r squared with respect to t, and this is implicit differentiation, so this is going to be 2r times dr dt. Okay. So if we simplify this a little bit, all right, we're going to get dA dt is going to be 2 pi r dr dt. Now what I find interesting about this is notice that the area, its rate of change with respect to t, is the circumference times the rate of r. This is c times dr dt. Just something interesting, okay? So that's how the rate of change of the area is related to the rate of change of the radius. All right, if we assume, like before, that the radius is increasing by 10 centimeters per minute, then we would use this, that the derivative of the area with respect to t is equal to 2 pi r dr dt. Okay, so notice here, we need to know what the radius, like at what length it is, right? So the rate at which the area is changing actually depends on the length of the radius. Okay, so that is actually kind of interesting, but when you think about it in terms of the graph here, right, as the radius increases, the area, the amount it increases each second is going to be increasing itself, right? So how fast the radius increases really depends on where the radius is. Is it at, say, 1? Or is it like at 10? Okay, so we already looked at the previous example when, say, when at t equals 1 minute, the radius is 18 centimeters, and at t equals 2 minutes, the radius is 18 centimeters. So in these two cases, we're going to get two separate answers here, because the rate of the area, right, at t equals 1, so I'm just going to put a 1 here, is going to be 2 pi r, which in this case is 8, times the rate of change, which we're still assuming is 10 centimeters per minute. Okay, so this is going to be 160 times pi square centimeters per minute. Now, where am I getting this square centimeters? Well, we have 10 centimeters here, and then this is 8 centimeters here in the radius. Right? The radius is 8 centimeters. So we have 8 times 10, which is 80, times 2, which is 160 centimeters squared per minute. All right. Similarly, when we find the rate of the area in minute 2, right, we'll have 2 pi times 18, and once again, that's where the centimeters live. All right, times, once again, 10 centimeters per minute. All right, which will be 360 pi square centimeters per minute. Okay. So what this means is that the rate at which the area is increasing, right? So you could almost think of that as acceleration being positive. All right, put more simply, as the rate of A, the rate of A is increasing as R increases. So as the rate of R, or as R itself increases, the rate at which A is increasing also increases. Okay, so let's jump to an actual example to show how this sort of stuff works. And I want to kind of give you an algorithm that you can sort of follow to approach these. It can be sort of overwhelming to try and tackle this sort of all at once. So what you want to do is try to break these problems down into smaller chunks that you can manage individually. Okay, so let's take a look at what this is asking, and then we'll take a look at how we can solve this. So it says, suppose an ice cube is melting at a constant rate of 0.25 centimeters per minute. At what rate are the sides of the ice cube changing when the sides reach 0.5 centimeters? Now, what we need to establish, okay, is what things are changing over time and what things remain constant. Okay, so to start off with, we need to ask ourselves what things are changing over time and what things are constant, what things remain constant. Okay, things that vary over time become variables. Things that remain constant we can fill in as constants. Okay. Now, another thing to note is when we do related rates, what we're often doing is taking a snapshot. I imagine it in like the Matrix, where they do the freeze frame and then they move the camera around to show, all the action in that freeze frame. That's sort of what we're doing. We're freezing this object at this particular second or minute or moment in time, freezing everything, and then taking a look at how all the items are moving around. And that's where this sort of, what's happening when the sides reach this 0.5 centimeters. Okay, so remember, we're looking at a snapshot in time. All right, well, what does that have to do with anything? Well, what that has to do with anything is that we need to differentiate before we plug in values for our variables. Okay. Now, this might seem a little counter to what I just said, because I just said things that remain constant can be filled in with constants. However, anything that varies, we don't plug that in yet. Right? So here, we're told that ice cube is melting at a constant rate, blah, blah, blah. At what rate are the sides of the ice cube changing when the sides reach 0.5 centimeters? We're not going to put 0.5 centimeters in immediately, okay, because the sides are changing. All right. So then, after this point, once after differentiating, then we can plug in the values and solve for the missing rate. Okay, so let me sort of explain what's going on with this example. Okay, so when I say we need to determine what's changing and what's remaining constant, well, what we have is an ice cube, which I'm going to attempt to draw here, but here's the ice cube. And then over time, it's melting, so it's getting smaller. Okay, so the sides, the nice thing about a cube is all the sides are the same. Well, the sides are changing. Okay, as is the volume. So the volume is everything going on inside, but the volume is also changing. All right, so these are going to be our variables. So now, I didn't mention this, but hopefully it's pretty clear. Now we need, and I totally messed this up because I just realized what I did here. When I say the ice cube is melting at a constant rate, it should be cubic centimeters, not centimeters. I do apologize for that. But what I was saying might be obvious is we need to find a formula that relates these quantities. Okay, and I know I need, well, the volume versus sides. Well, when we're talking about a cube, okay, it's basically got sides, it has surface area, and it has volume. I don't really care about surface area because we haven't been given anything in terms of surface area. What we've been given instead is a rate for the volume. This cubic centimeters, that's going to be our dV dt. Okay, so we need a formula that relates these quantities, and thankfully that's going to be V is equal to S cubed, right? The length times the width times the height, S cubed. Now, notice the first thing I said was we need to figure out what's varying and what's constant. Well, both of these are varying, so there's nothing to plug in. Okay, so instead, we'll just differentiate with respect to t. Okay, so it'll be the derivative with respect to t of v is equal to the derivative of with respect to t of s cubed. Okay, so we'll essentially just get dv dt, okay, is equal to, now the derivative of s cubed with respect to t, again, remember we're doing this implicitly, so this is going to be 3s squared times ds dt. Okay, so this is the formula that relates the rate of v to the rate of s. All right, so now we can start plugging in what we have. So here is a rate at which an ice cube is melting. So that's 0.25 cubic centimeters per minute. Okay, and then we're asking how are the sides changing when they reach 0.5 centimeters. So this is our S at the moment in time. Okay, it's the matrix situation. So we're freezing time when the sides reach 0.5 centimeters. So this is going to be S at the freeze frame time, and this is going to be our rate of change of V. All right, so if we plug in what we have, so dV dt, well, we need to be careful. Since it's decreasing, right, it's melting, we need to put it in as a negative rate. So it's going to be negative 0.25 cubic centimeters per minute. Right, so this is our dV dt. And then it'll be 3 times our S, which in this case is 0.5 centimeters. And then we square the whole thing. And then ds dt. This is what we're looking for. That's what we're asked to find, right? At what rate are the sides of the ice cube changing? oh, at what rate are the size of the ice cube changing? That's going to be ds dt. Right? So that's what we're looking for. So this is what we are trying to find. Right? And it should just be a matter of simplifying what we have and solving a basic equation. Right? We'll have 3 times 0.5 centimeters squared, so that should be 0.25 centimeters squared. And I should clean this up a little bit. There we go. Now it's not taking up so much room. And then 3 times 0.25 is going to be 0.75 centimeters squared times ds dt. And now we just divide both sides by 0.75. Okay? And when we do this, and sorry, that's a centimeter squared there. One nice thing about doing this with the units, we'll see that they cancel correctly. Centimeter squared cancels with 2 of these and leaves just a centimeter. So we end up with 0.3 repeating centimeters per minute. And that's our ds dt. Okay, so the sides are decreasing at about 0.33, let's use 2 significant digits here, centimeters per minute. Right, so the sides are decreasing by 0.33 centimeters per minute at this very moment, and I always like to write this just because that's the moment we're talking about. That's not what's always happening. Right? In fact, things will probably be different at different lengths of our sides, but at this moment, they're decreasing by 0.33 centimeters per minute. All right, for this next example, I think it's pretty much against the law to not cover this in a calculus class. This is the falling ladder problem. Okay, so suppose we have a 5-foot ladder leaning against a wall, right, and the top of the ladder begins to slide down, right, and we want to find how fast the base of the ladder is moving along the ground at a certain point. Okay, so say we have this ladder here. It's leaning against the wall. And as the ladder, so the ladder is 5 feet. I mixed these up, didn't I? Let me say it's 5 meters. Okay, so it's 5 meters. Okay, and as the top starts to slide down, the bottom starts to slide away from the wall, right? Because if once, say, the height hits this point, in order for the ladder to remain the same length, as the top moves down, the bottom has to move out. All right, to kind of show you on a graph through an animation what I'm talking about, if we have a ladder, let's move it over just a bit here, but we have a 5-meter ladder, and the height is decreasing, so the top of the ladder is falling at a constant rate. As that happens, okay, the length from the base to the wall is sliding away, and you can see that the way I have the animation set up and the way this problem is, the height is decreasing at a constant rate. All right, we see that. However, as that happens, this rate is actually sort of changing. It's going real fast at first and then starts to slow down, okay, as the ladder gets closer and closer to being flat on the ground. Okay, so all right, so we're told that the top of the ladder is sliding down at a rate of 0.2 meters per second. So this distance here is changing, and I'm going to put negative 0.2 meters per second here. Okay. Now we want to know how fast is the base of the ladder moving along the ground when the top of the ladder is 3 meters above the ground. So we want to know, all right, what is this rate here when the height of the ladder, or the top of the ladder, is 3 meters above the ground. So at the moment that the height reaches 3 meters, we want to know, well, this rate is always the same, but we want to know how fast are we going in this direction. All right, so this is where I say that we are going to be talking about, okay, what remains constant and what changes, right? So this length here, the length between the base of the ladder and the wall, I'm going to call that x, and the height I'm going to call y, just to line up with the x and y axis. Okay, now these are changing over time, right? If we go back to our graph, the y value is changing over time and the x value is changing over time. What's not is the length of the ladder. The length of the ladder is constant, right? So that length, unless the ladder decides to fold up as it's falling, it's not changing. Okay, so that's the constant in the situation. Okay, so this is the thing not varying. These two things vary. So we need to find a formula that relates x, y, and this 5 meters. And if you'll notice, this is a right triangle. So the length of the two bases and the hypotenuse we can get from the Pythagorean theorem. Okay, so from the Pythagorean theorem, 5 squared is equal to x squared plus y squared. So we get 25 is equal to x squared plus y squared. Okay, so this is what I mean by you can put in constants now, things that don't vary. However, notice I'm not putting the 3 in. Okay, we don't put the 3 in until later because this is that moment in time that we're freezing to see what the rate is. Okay, so now what we're actually looking for is dx dt, and what we're given here is dy dt. Okay, so now we will differentiate everything with respect to t. So when we differentiate 25, that's of course 0. When we differentiate x squared, remember we're differentiating with respect to t. So this is going to be 2x times dx dt. Okay, and then now we'll differentiate y squared with respect to t. So that's going to be 2y dy dt. All right. So now we can, I'm going to start by dividing everything out by 2, just to get rid of the 2, because 0 divided by 2 will still be 0. So we get 0 equals x dx dt plus y dy dt. Okay, now we can plug in all the stuff we have and find the things we don't. Okay, so 0, we don't need to mess with that. X. Well, let's actually start over here with the y's because we know what y is. Y is 3 meters and dy dt is negative 0.2 meters per second. Okay, so that's our y and our dy dt. Now, dx dt, that's what we're actually looking for. Okay, this is what we're trying to solve, so we don't have that yet. But what is x? We weren't given x. We weren't given this length. However, we're looking at the moment when y is 3 meters, the hypotenuse is always 5 meters, and we want to find what x is. We can also use the Pythagorean theorem, right? Because 25 is going to equal x squared plus y squared, which is 3 squared, which is 9. Okay, so when we subtract that over, we'll get 16 is equal to x squared, so x should be 4 meters, thanks to the Pythagorean theorem. So sometimes you might have to do a little extra work around here to get what one of the other variables is, but we'll have 4 centimeters, and this whole thing is equal to 0. Okay, so now what we have is 4 centimeters times dx dt. Sorry, that should be a dt there. Okay, plus this 3 times 0.2. That's going to be a minus 0.6 meters squared per second. All right, that might not make much sense, but if we're going to solve for this dx dt, we're going to move this over now to get 0.6 square meters per second is equal to 4 centimeters times dx dt. I will note that you don't have to put in your units, but I often like to, and I prefer to do it correctly. I don't know why I just put centimeters here. That's meters. I like to do it correctly so that when I get to the end, if my units don't line up, it's a good sign that I did something wrong. Okay, so now we'll just divide by the 4 to get 0.6 square meters over seconds divided by 4 meters. So one of these meters cancels up top, and that should make some sense because dx dt, well, x is a length, so that should be meters, t is a time, so that should be seconds. All right, so dx dt is 0.15 meters per second. All right, so at this moment, the base of the ladder is moving at about 0.15 meters per second. And there we go. Let's take a look at another example. All right, let's say we have a conical coffee filter. So coffee is draining out of a conical filter at a rate of 2.25 cubic inches per minute. And if the cone is 5 inches tall and it has a radius of, let's just have one of there, of 2 inches, how fast is the coffee level dripping when the coffee is 3 inches deep? Okay, so let me kind of draw a picture here to kind of describe what's happening. So we've got a conical filter. Okay, we are told that it is 5 inches tall and has a radius of 2 inches. Okay, now coffee is draining out of the filter, right? So it's dripping out. So as that happens, we have basically a smaller cone within a bigger cone, right? And the coffee level is going down, the water's leaving, and so what we're told is that coffee's draining out of the filter at a rate of 2.25 cubic inches per minute. So we know how the volume of this mini cone is changing. So this is the rate, the volume of the mini cone is decreasing at. Okay, so this is a volume, I know that because it's cubic inches, right? So this is basically our dV dt. And our dV dt is negative 2.25 cubic inches per minute. All right, so that's what's happening here. And now we're asked how fast is the coffee level, so this is important, the coffee level dripping when the coffee is 3 inches deep. So this is the coffee level, its height essentially. So this we could call, say, H, okay? And we want to know how it's basically decreasing as the volume is decreasing. All right, so basically this is find dH dt, okay, when when H is 3 inches deep. So we're concerned about when it's at 3 inches. Okay, so the volume of a cone is 1/3 pi r squared h. Okay, so the volume is related to the height of the cone and the radius of the cone, and that's what's going to be kind of tricky here. All right, that's what makes this problem kind of tricky, because as given, without any more information, when we differentiate this, or dv dt, we'd have to do a product rule. So we'd have 1/3 pi 2r dr dt times h left alone plus 1/3 pi r squared dh dt. Okay, now this is what we're looking for, the dh dt. However, we don't know anything about r necessarily, or dr dt, or what have you. So maybe there's a way we can simplify this. Right, and it turns out there is. Because we have a cone within a cone, we can compare these with like triangles. Right, we have the bigger cone, oops, ran out of space there. The bigger cone, which is a 5x2 right triangle. And then we have the smaller cone, which is an h by r triangle. Right, so r over h will need to be equal to 2/5 using similar triangles. Right, never thought you'd use that again, huh? So in other words, r is equal to 2/5 times h. Okay, so if we plug this in for r, okay, we can have this in a form that is only in terms of h. Right, so that will definitely simplify our lives a lot. All right, so v is going to be 1/3 pi. R I'm going to replace with 2/5 h all squared times h. Now, I will mention there are ways we could do this without simplifying it this way, but it's going to be a lot easier because we'll avoid using the product rule when we do this. Okay, so this is going to be 4/25 when we square it, right? Which when we multiply that by 1/3, we'll get 4/25 pi, and then h squared times h will give us h cubed. So now we've gotten v completely in terms of h. Right, so that's just going to make our lives a lot easier. Now notice, nothing's really a constant, because as time goes on, the radius and the height change. Right, the radius and the height are both decreasing. So we can't do that nice little thing where we plug in a constant and simplify it, but we did plug in a relation to simplify it. Okay, so anything you can do to simplify your stuff ahead of time is going to be great. And that, I'm sorry, is a 75, not a 25. That kind of looked like a 2. All right. Now we will differentiate both sides with respect to t implicitly, so we'll get dv dt is equal to 4/75 pi times, now this h cubed, that's going to become 3h squared dh dt. All right, and the 3 is going to cancel with the 75 and get us back to 25. Okay, so to clean this up a little bit, dv dt is equal to 4/25 pi h squared dh dt. And now we have everything we need, because we have dv dt, that's here. We have h, and we want to find dh dt. Okay, so this is what we're trying to solve for. All right, so this is what we want, and these other things are what we have. So we're going to go and plug in everything we have. So dV dt was negative 2.25 cubic inches per minute. We have 4 over 25 pi. And then h, jump up real quick to see the problem, is 3 inches. Okay, so we'll get here 4 over 25 pi times 3 inches all squared dh dt. So that's going to be 9 inches squared. All right, so when we put this all in, we'll get about 1.44 pi square inches dh dt. We'll divide this over to get that dh dt is equal to negative 2.25 cubic inches per minute, all over 1.44 pi. I'll have the pi there just to keep things sort of as exact as possible for a minute. But these square inches here are going to cancel with the inches cubed and just leave inches per minute, which is exactly what we expect to happen. All right, and then when we plug this in the calculator, we get that the rate of the height at this moment is going to be negative 0.497 inches per minute. All right, now be careful when you plug this in that the whole denominator is in parentheses so that you don't forget that the pi is there. Okay, and there we go. All right, so for this example, I'm going to show you how trig can be incorporated into related rates. So this usually has to do with angular velocity, or how things are spinning around or whatnot. So here we have that an observer stands 200 meters from the launch site of a hot air balloon at an elevation equal to the elevation of the launch site. So that's just saying you don't have to take into account the height of the viewer versus the height of the launch site. Okay. The balloon rises vertically at a constant rate of 4 meters per second. How fast is the angle of elevation of the balloon increasing 30 seconds after launch? So, to describe what's going on here, we have an observer, okay, who we know is 200 meters from the launch site. We have the balloon, right, that's increasing by a constant rate of 4 meters per second. Okay. Now what the angle of elevation is when the observer is looking at the balloon, the angle of elevation is this angle made between the elevation of the balloon and the ground, essentially. So we're creating a right triangle. Okay, so that's what it is we're talking about. Now, what are the things that are changing, right? As the balloon increases, so after, say, a couple of seconds, it's here, right? So this height, which I'll call y, is increasing, okay? And this angle is increasing, right? Because as time goes on, the angle, right, as the balloon goes up, the angle of elevation is also increasing. All right, to give a little impression on a graph here, as, say, if the balloon is right here and it starts to rise, we see that as long as it's going like straight up, the angle of elevation is increasing as the height increases. Okay, now this is in degrees because that's what my graphing software wants to do, but we'll be looking at it in terms of radians. But so these are the things that are essentially moving. We don't really care that much about this. We can solve this problem based on just the information that we have here, because we have a right triangle. We want to know how the angle of elevation is increasing, right, what its rate is. So basically we're looking for d theta dt. Okay, and we're stuck in a right triangle, and we have the side adjacent and the side opposite. Okay, well, the quickest way we can do that is with tangent, right? Because tangent of theta is equal to the side opposite over the side adjacent. Okay, well the side opposite, that I'm going to call y because that's changing over time. The side adjacent is fixed. It's a constant, so I can put in 200. Right, so our related formula is tangent of theta is equal to y over 200, or if I want to make it a little easier on myself, move that 200 over to say that 200 tangent theta is equal to y. That may not be necessary, but that looks a little nicer to me. Now, when some students do this, I see that they start trying to solve for theta. We don't have to do that at all because of the chain rule. Right? And why is that? Well, if we just start differentiating both sides with respect to t, right, we'll have 200 times the derivative of tangent theta with respect to t. It'll be derivative of tangent theta. And that will be equal to the derivative with respect to t of y. Okay, so the 200 comes along for the ride. The derivative of tangent is secant squared theta, but then we need to multiply by the derivative of the inside, which in this case is going to be d theta dt. Right, and the derivative of y with respect to t, that's just dy dt. All right, and that is kind of perfect because this is what we need. Right, that's what we're looking for. We're given this, dy dt we know is 4 meters per second, and we can find secant theta. Okay, so we can find everything we need now, and we don't have to solve for theta. Okay, so here's how we proceed. Notice this piece of information they gave us that we haven't used yet. Right, we want to know what's happening 30 seconds after launch. Okay, well 30 seconds, if the balloon's traveling at 4 meters per second, right, so if we're traveling at 4 meters per second, after 30 seconds, we should hit 120 meters. Right, just multiply these two together, the seconds will cancel, and so what we essentially have here is a right triangle that is 200 by 120, and we want to find secant of this angle. Right, and to get that missing piece, we can use the Pythagorean theorem, right, which won't come out to be something even, but it's about 233.23 meters, let's say. All right, and so secant is the reverse of cosine, right? So it's going to be, instead of adjacent over hypotenuse, it's going to be hypotenuse over adjacent. So it's going to be 233.23 over 200. And we're going to square that. Okay, now what's interesting here is how the units are going to interact with one another. Okay, so notice that these two values here are meters, which are going to cancel. So we won't have any units here. However, this 200, if we go all the way back to here, this would be y meters, 200 meters. So this 200 is the thing that's in meters here. Okay, and we have d theta dt. And then dy dt was 4 meters per second. All right. So we can simplify this a little bit, which when I calculated this out, I got about 271.98 meters times d theta dt is equal to 4 meters per second. Right, and then we'll divide this through to get that d theta dt is 4 meters per second over 271.98 meters. Okay, the meters cancel, and we get about, it's about 0.0147 or 15-ish. okay? But notice the meters cancel, but we have still the per second. So what's happening? Well, whenever this happens with, say, a theta, this actually ends up being radians per second. Because what ends up happening with, say, angles, if you've ever heard in your, say, your trig class that angles have dimensionless units, that's essentially what's happening here. The angle is not really a length or anything like that. It's the amount of how much something spins around. So in cases like that, the length units are going to completely cancel each other out, and then we'll be left with just radians per second. All right, so that should be enough to get you started on the homework. I do plan to come back in a part 2 of this particular video with just more examples, okay? But we do have the setup for how all these problems are going to work. It's just a matter of now maybe seeing some more examples that are a bit more complicated. Okay, so I'll catch you all in that video. Talk to you then.